the end of the last video, one of the things that's important for probability is being able to count. So what we're going to cover from now are essentially counting principles. Okay, so here we're going to cover some ideas which aren't necessarily really from probability. They're more to do with, say, counting, combinatorics and other areas of pure mathematics, or discrete mathematics, but they're quite useful concepts in probability for the following reason. Okay, so if we consider a probability space, okay, or a sets of sample space, okay, and we suppose that on that sample space, if each outcome, so each thing that can happen, each individual outcome that can happen, is equally likely, okay, i.e. that the probability of an outcome omega is some constant p, and that constant's the same obviously for all of the outcomes in our sample space. Okay, and just to remind you that this means this symbol like this means for all, and this symbol means belongs to. Okay, so a little bit of mathematical notation there. All right. Now, since probabilities are positive and sum up to 1, okay, for each outcome, then since we have these probabilities, if we sum up all of the outcomes in this sample space, since that must sum up to 1, okay, it must be that we can specify the probabilities of each outcome. It must be given by 1 over the number of elements that we're summing over. Since we're summing over each element of this set, okay, the sample space, and it must sum to 1, the only way we can get that to sum up to 1 and all these being equal is to have this as your probability. Okay, so in order to work out the probability of a specific outcome, then we need to count, okay, the number of elements in this set. So just to mention, these straight brackets here mean we look at the number of things inside this set omega. Okay, it's sometimes called the cardinality of the set. Okay, which is just a fancy way for saying the number of things in omega, really. Okay, a further point that remember that if we wanted to know the probability of an event, so remember an event is a set of outcomes, so if we want to know the probability of this set of outcomes occurring, then we get that by summing up all the outcomes within the set A, okay, and the probabilities for each of those outcomes. Okay, so, and this is true for any subset of our sample space. Okay, so, well, if all these terms are equal to each other, equal to 1 over the size of the set omega, then the probability of the event A is just equal to the number of items in this sum, since these are all equal, divided by the probabilities, which is just 1 over the number of elements in the sample space. Okay, that makes sense. All right, all things are equally likely, and there's this many of them, so that should be the proportion of time that we expect an outcome in event A to happen. Okay. So basically, for this reason, because of this rule up here, okay, counting, being able to count the number of elements in a set A or a set omega is important in probability. Okay. Okay, so we're going to break this down into pieces now, different rules or ways that we can go about counting. Okay. Okay, so the first one, 0th and most obvious one, is going 1, 2, 3, 4, and so forth. Okay. But we can do a little bit more than that, so let's do that now. Okay. And one thing I should say is, really, when I say probability here, I'm really meaning discrete probability. Okay, it's a slightly different ball game when we get into continuous sample spaces. Okay. Okay, so we are going to cover now rules for counting, or some rules, formulas, / principles. Okay, so one, which will start easy, is just multiplying. Okay. So that's where you have an outcome for each row and column entry, and then we multiply together to get the total number of entries. Okay. Then we'll cover factorials. Okay. This will be like the number of ways you can reorder a set of items. Permutations. Okay, and that will be the number of ways we can lift out a certain number of items in a certain order. Combinations. Which are sometimes also called binomial coefficients. Okay, and that's ways that we can take out number of ways we can take out items where we don't mind about the order. Okay, and then multinomials. We can think of that as the number of ways that we can put several items into several bins. Okay. And so how are we going to go about doing this? So I've always found it a bit of a difficult one to teach. There's quite a few ways of people get kind of muddled between the differences between these different concepts, and even I do, depending on the way that the question is phrased, which we'll talk about more in a minute, and I'll try to do more examples in a later video. Okay, but we're going to do it by considering a single example that we can kind of sort of develop through these 5 concepts. Okay, so we do so meaning cover these concepts. We do so by considering the following setting. Okay, so we're going to consider a card dealer has 5 cards. So let's keep it simple, not too many cards. Has 5 cards. He's got an ace, a king, a queen, a 4, and a 2. All right, and you are dealt 3 cards. And you win if you get ace, king, queen. Okay, so that's essentially the setting that we're considering, and what we're going to be interested in is the probability that you win. Okay, now the thing is, the probability of winning depends on how or more to the point, what we really mean. Let's say that what we mean by the cards being dealt and what it means by ace, king, queen. Okay, so one of the issues that people sometimes have with these sorts of questions is it's not always very clear. You have to be quite careful about how you read the language with these sorts of questions. Okay, so in fact it's a little bit of an ill-posed problem here, because when I say we deal 5 cards, does that mean that I get dealt 3 cards? Does that mean that the dealer shows me a card, puts it back in the deck, shuffles, shows me another card, puts it back in the deck and reshuffles, and then shows me a 3rd card? Okay. Or it could alternatively mean that out of these 5 cards, the dealer lays out 3 cards in sequence, okay, and then puts them on the table without replacing them back in the deck. Okay, those are 2 different ways of dealing the cards. Okay. Also, it could be different by what we mean to get ace, king, and queen. It could mean I need ace, and then I need to get a king, and then I need to get a queen. Okay, so in the order that the cards are dealt, I need to get first an ace, then a king, and then a queen. Or it could mean that we just need ace, king, queen in any order. Okay, probably if the way that question was phrased, you're probably guessing that what we really mean is that the dealer's going to deal out 3 cards without replacing them back in the deck, and getting ace, king, queen in any order will mean that you win. Okay. However, to get to the calculation for the probability of winning under that circumstance, we have to think a little bit about how to count the number of ways which you can deal out 3 cards under that system. Okay. So we'll start with the easier case, which is a little bit more ad hoc, and we'll work towards the case that we really think the answer should be within. Okay, so in each case I'm going to sort of specify a bit more the rule by which I mean the dealer deals the cards, and the rule by which I mean that you win. Okay. Okay, so first, multiplication as mentioned up here. Okay, so we're going to consider multiplication. Actually, I'll tell you what, I'll start a new page. First, let's consider multiplication. Okay, and this is the case where the dealer replaces the cards back in the deck, reshuffles, and gives me another random card. Okay, so the rule that I'm really considering here within that framework above is, I suppose, okay, the dealer replaces each card reshuffles, okay, and then deals a new card. shows a new card. Okay, so we take the 5 cards, the dealer shuffles them, shows me one, okay, puts it back in the deck, shuffles, shows me another, puts it back in the deck, shuffles, and then shows me 3rd card, and then puts it back in the deck. Okay, what it means to win, and you win if you get an ace, and then in the 2nd card you get a king, and then you get a queen. Okay, so conceptually let's think about it like this, and I'll draw a few pictures as we go along. Okay, so what I'm thinking of here is that really I have 3 slots for my 3 cards. I have card 1, card 2, and card 3. Okay? And I could get, I'm looking for ace, king, queen, but I could equally get 4, 2, okay? And then also I could get a further 2, because I could get a 2 twice. After reshuffling I could get the same card again. Alright? So then we think about, well, what could happen? Okay? For the first card, okay, that I'm given, the dealer has 5 cards. Okay, so let's start at sort of time 0. Okay, and let's draw a kind of a tree of what could happen. So the first thing that could happen is that I go to state when my first card that I'm shown is an ace, for example. Or, alternatively, I could be shown a king. Okay? Or, alternatively, I could be shown for that first card a queen, or a 4, or a 2. Okay? So ace, king, queen, 4, or 2. Alright, so there's 5 things that can happen out of that first card. Okay? 5 things that can happen. Okay? Now look at the second card. Well, the fact I got an ace in the first card doesn't affect anything to do with what happens with the second card. So once again, if I look at the number of things that can happen after having an ace, there's 1, 2, 3, 4, 5. Ace, king, queen, 4, and 2. Similarly here, there's 5 again. And I'm going to be bad at drawing, so I'm going to skip these ones and get to the last one. 1, 2, 3, 4, 5. Okay, well, I'll try to draw those. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so now for each of the 5 branches here, I've got a further 5 here. Okay, so in total, that's going to make 5 times 5. Okay, so I've got 25. Okay, ways of choosing 2 cards. Okay, then within each of these branches, so that gets me to the second card, and now I can think about what happens with the number of things that could happen for the third card. Okay, and again for each leaf of this tree, okay, I get a further branching and get a further 5 cards. Okay, so for each of 8, for say the outcome where I get an ace and an ace, so 5 further things that with equal likelihood that could happen to the third card. Okay, so if I think about what's going on here in terms of this tree, if I drew it out, okay, I would end up with 5 times 5 times 5, okay, different ways to go from time 0 to time 1, 2, 3 when the dealer's dealt the third card. Okay, so there's 125 things. 5 times 5 times 5. Well, let's say there are 5 times 5 times 5 ways of dealing these cards. Okay, so indeed since no one of those outcomes as listed here along these trees is any more likely than any other, the probability that I get ace, or let's say the probability I win, where win means I get this is an ace, this is a king, and this is a queen, okay, is equal to 1 over 5 times 5 times 5, which is equal to 1 over 125. Okay? So this is something that's generally true. Notice really what's happening here is that the probability space that we're considering, okay, sorry, the sample space that we're considering, okay, is really like a kind of let's say a sort of Cartesian set. So we've got card 1, we get card 2, and I write it, and then card 3, okay? And the outcome is specified essentially by this vector where each coordinate of the vector is the outcome of the card, okay? So card 1, card 2, and card 3 can be equal to any of ace, king, queen, 4 or 2, okay? Or another way to write this would be to think of it as I have the set ace, king, queen, 4, 2, okay? And we're taking the Cartesian product of those 3 times, okay? And the size of that is equal to the size of this set to the power of 3, which is 5 to the power of 3. Okay? So that's something that's true in general. Okay? So, in general, if your sample space is really the product, okay, of smaller sample spaces, we could think of each of these as being a small sample space, I equals 1 being the first card, I equals 2 being the second card, okay, and then the size of this set is just the product of the sizes of the smaller sets. Okay. Right, so that kind of covers what happens when we replace the cards after we've dealt them. So so the dealer deals one card and then replaces it, and then deals another card and then replaces it. Okay, and because of this kind of refreshing, we essentially get this kind of product structure. Okay, which then means the number of items in that set is a product. Okay. Okay, so that's somehow the easiest way of counting. Okay, we just have rows and columns and so forth, and then we can count. Okay, now let's just sort of twist this problem a little bit, not too much in fact, okay, in order to consider factorials. Okay, so the rule I'm just going to change a little bit. I'm still going to have the same setting where I replace the cards back in the deck, okay, after dealing them. So we suppose the dealer, okay, takes the card back, or let's say replaces the card back in the deck and reshuffles. Okay, and you win, okay, if you get ace, king, queen, but in any order. Okay, so the key difference between the previous example and this example is in the previous example I needed to get ace, and then I need to get a king, and then I need to get a queen. So my card number 1 had to be an ace, my card number 2 had to be king, and my card number 3 had to be queen. Now, okay, it doesn't matter which order I get those cards in, okay? So if I draw my picture again, here's card 1. Here's card 2. And here's card 3. Notice that getting a queen and an ace and then a king, quack, is still a winning combination. Okay? And we know that this outcome, okay, has exactly the same probability of getting ace, king, queen. Okay? There's no difference, it's just another branch in that tree from before. So the probability of winning is 1 over 125 again. Okay? So now, the issue is there's more than one way that we can win. Okay? So now, there is more than one way to win, i.e. the event that we're interested in, the event that we win, okay, the size of that set is now bigger than 1. Okay, so we have to count the number of elements, the number of ways we can win. Okay, so let's have a think about that. So what size? So if we're going to try and find the probability of winning, remember we need the probability of winning is going to be the number of events in which you win divided by the total number of the number of outcomes where you win divided by the total number of outcomes. Okay, so that's just this formula, just skipping up here. Okay, so we know this, but we don't know what that is, the number of outcomes where you win. Okay, so we need to determine this. Okay, we need to find this number. All right, and we could do something similar. We could draw a tree again. That's one way of thinking about it. Okay, so let's say we're at time 0. Okay, we're waiting for the dealer to deal us a card. Okay, and then we draw the 3 things that can happen. Okay, from there. So first, okay, we could get an ace from the first card, or we could get a king from the first card, or we could get a queen from the first card. Okay, and then now let's suppose that we're now at time 1. Okay, and we've had an ace. Okay, so let's suppose that the first card here, so just rubbing these, well, let's leave it as it is. I'll tell you what, why don't we do the queen branch anyway? Suppose we're in this situation. Okay, a queen has just been dealt to my let's suppose there's a queen here. Okay, what things are permissible to happen and I can still win? Okay, well, if I get another queen, that's not going to help. If I get a 4, it's not going to help me win, and if I get a 2, it's not going to help. There's only 2 things that can happen after I've been dealt a queen where I'm still on track to be able to win. Okay, the first is that I get dealt an ace. Okay, and the second of those is that I then get dealt a king. Okay, I can't get dealt a queen anymore because that would mean I didn't get ace, king, queen. Okay, and so now, so rather than having 3, so unlike here where we had 3 branches coming out, here we've now got 2. All right. Similarly here. Okay, so what we're left with is ace and queen, and here if we've been dealt an ace, we've got a king and a queen left. Okay. Now, let's suppose we're in this situation. We've been dealt a queen, and then we've been dealt an ace. There's only one thing left that can happen that would allow us to win, and that's that we're dealt in the next round a king. Okay. Similarly, if I've been dealt queen, king, the only thing that can happen is to be dealt an ace. Okay. Here, it's going to be queen, ace, queen, king. Okay, so I can count out the number of branches that have happened in this tree just like before. Okay, and then, so in particular, you can notice there's 6 branches. In particular, there's 3 branches to start with, and then it splits, each of those split into 2 branches, which then splits into 1 branch, which gives me the 6 branches that I have. Okay? In other words, the total number of outcomes that can occur where you win, okay, is 6. So therefore, the probability that you win, the probability of winning, is equal to 6, so the size of this set is 6, divided by 125. Right? Okay? So, something happened there. We had to consider something that wasn't the same as this multiplication before, where it was just 5 times 5 times 5, but now it's a special kind of multiplication. We're going 3 times 2 times 1, so decreasing each time by 1 increment. Okay, and that's what a factorial does. Okay, notice what this counting did is counted all the ways I could take these 3 cards, ace, king, queen, and reorder them. Okay, so it's the total number of ways that I can order ace, king, queen, okay, into 3 different positions. Okay, now this sort of multiplication is called a factorial. Okay, it's got a special name for it itself. Okay, so we'll just write down a bit of a mathematical definition for that. So definition. Okay. For a number, n, which could be 0 or 1 or 2, or any positive integer, n factorial, so we could say 5 factorial or 7 factorial, is written as n exclamation mark. Okay, so we say n factorial and write this, and it's equal to n times n minus 1 times n minus 2 all the way down to 1. Okay? And one thing to add is that you'll notice that we can do this for all of these numbers except for 0, and to add that 0 factorial is by convention set equal to 1. Okay. In some sense it's set like that because all the maths works out nicely when you do that. There are also kind of deeper reasons for why that's the case when you do your sort of complex analysis maybe later on, but that's a different story. Okay, but the story that we're trying to mention now is that really what this n factorial is doing, okay, is it's counting. So n factorial counts the number of ways we can order a list of n, well, let's not say list, let's say set. A set of n items or n elements. Okay, so what do I mean? So here I had a set that consists of ace, king, and queen, and the number of ways I can order them is, well, ace, king, queen, ace, queen, king, so this branch, king, ace, queen, king, queen, ace, queen, ace, king, and queen, king, ace. Okay, so those are all the ways I can go about ordering these 3 elements. Okay, and that's given by 6 factorial. Okay, I mean 3 factorial, sorry, 3 factorial. Okay. Okay, so that's a bit of a building block on the way. So that's the total number of ways we can order. We can order n elements is given by n factorial. Okay, so again, that's a useful counting rule.